Hello, everyone, and welcome back to Aviation Physics. I'm Dr. Chen, and today we're going to step back from specific topics like forces or kinematics and focus on scale that underpins everything we do in this course: problem solving. Many students find physics challenging not because they can't understand the concepts, but because they aren't sure how to approach a word problem from a blank page. Today, we will build a structured framework to tackle any problem systematically. As always, here is my contact information, so please reach out if you have any questions. Go Dolphins! Solving physics problem effectively requires strategy. If your approach so far has been to find a formula in the textbook that looks like it has the right letters and then plug in numbers, you will find that method starts to fail quickly as problems get more complex. The real goal here is to focus on understanding the core concepts first, rather than just memorizing equations. We want to develop your critical thinking and problem-solving abilities. These skills are essential not just for passing this course, but for your future careers in aviation, where you will constantly be facing with complex situations that demand clear analytical thinking. To help us organize our approach, we will use a framework called IDEA. These four letters breaks down the problem-solving process into four distinct steps. First, identify. Read the problem carefully and identify the fundamental concepts involved. Is this a force problem? A conservation of energy problem? Then explicitly write down your known quantity and what you need to find. Second, develop. This is where you plan your attack. Draw a diagram, like a free body diagram, or a sketch of the situation. Choose a coordinate system. Identify the physical principles or equations that connect what you know to what you need to find. Third, evaluate. Now you execute the plan. This involves manipulating your equations algebraically to solve for your target variable before plugging numbers. Once you have isolated the variables, perform the calculations carefully, making sure to keep track of your units. Finally, assess. Review a solution. Does the answer make sense? Is the order of magnitude reasonable? Does the units match what you expected? This step helps you catch errors and solidify your understanding. Now I want to highlight a few common mistakes students make when trying to use this framework. The most common oversight by far is skipping steps. Many students want to jump directly from identify to evaluate. They skip drawing a diagram during the develop phase. This is a critical mistake. The diagram is where you translate the words of the problem into a physical model. Skipping it often leads to some errors or incorrect force components. The second common oversight is skipping the assess step. Once you get a number, it's tempting to circle it and move on. But taking a moment to reflect on whether the answer is logical deepens your understanding far more than just getting the equations right. Before you even write down the first equation, let's talk about the mindset and the initial setup. First, stay calm. It's easy to look at the complicated problem and feel overwhelmed. Take a breath and trust the process, like flying. Problem solving becomes more familiar and intuitive with regular practice. Always visualize the problem by drawing a diagram before you do any detailed calculations. Try to estimate a rough answer. If you are calculating the range of a projectile, do you expect it to be a few meters or a few kilometers? This initial benchmark helps you catch significant errors later on. Alright, let's get into the nitty-gritty of the evaluation step. Here is a professional tip. Delay substituting numbers for as long as possible. Solve the problem using variables first. This reduces calculation errors, and often variables will cancel out, simplifying the problem significantly. Pay close attention to details. Choose your coordinate system wisely to simplify the math. Clearly distinguish between vectors and scalars. Force and velocity have directions, while mass and time do not. Use clear variable names. Don't use V for both initial and final velocity. And please, work neatly. If you can't follow your work, I cannot give you partial credit. Now let's expand on the assess phase. You have an answer. How do you know it's right? Follow those steps. The first thing you can do is do dimensional analysis. Check your unit. If you are calculating a distance, your final units should be meters, not meters per second. If you don't match, you made an algebraic mistake somewhere. The second thing you can do is order of magnitude estimate. Is your answer reasonable? If you are calculating the mass of an airplane to be 5 kilograms, you have probably make a mistake somewhere. Then we can test limiting cases. This is a powerful technique. If your equation describes motion on a ramp, what happens if you set the angle to 0? Does your formula simplify to the case for flat ground? It should, right? So this critical reflection is what builds true expertise. Let's walk through a simple example using the IDEA framework. The problem is simple. A ball is dropped from rest from a height of 20 meters. Find the time it takes to hit the ground. Identify the problem. The concept is free fall, which means constant downward acceleration is g equals 9.8 meter per second squared. Our knowns are initial height, h equals 20 meter, and initial velocity v0 equals 0. It's not given in number, but given in words. Because the problem said the ball was dropped. The unknown, what do we need to find? We need to find the time, so the unknown is t. And then need to develop a equation to write this. We need a kinematic equation that relates displacement, initial velocity, acceleration, and time. The best choice is displacement equals initial velocity times time 1/2 at squared, which will, in our situation, because initial velocity is 0, so drop height is 1/2 gt squared. And then we need to evaluate this problem, substituting the numbers. Now we can just plug all the numbers into this. 2 times 20 divided 9.8 give us 2.02 second. Does 2 seconds seem reasonable for an object falling 20 meters, about 6 stories? Yeah, that sounds like it in the right ballpark. So you need to work it out correctly to seconds. So the solution looks solid to me. To wrap up, a structured problem-solving strategy like IDEA simplifies complex problems by breaking them into manageable steps. It helps move you beyond simple formula memorization to comprehension. Like any skill, become a good problem solver requires regular practice and honest reflection on your process. Apply these methods constantly and consistently, and you will improve not only in this class, but in all your future technical work. Thank you, and I will see you in the next lecture.